You got to learn terms, exactly what you said. And that's the whole big thing. The big thing, one of the big things, a lot of big things, but the terminology. And that's what I guess that's what makes us special, is because we come up with our own language. And you Army guys have your own language. Us Navy guys have our own language. And, you know, we're both in the military, but our language is different. And if you think about it that way, what we're using, the vernacular that we're using, and we've got to learn the language. Once you get the language down, it's not really all that complex, really, when you do that. And again, after you screwed enough stuff up and had to fix it, it becomes a lot clearer when you do that. It's something that is not going to be magically, it's not going to magically going to say poof and yeah, I got it, I understand all of this stuff and it works for me. It takes time to assimilate. And what you have when you get done with these courses, you got a lot of knowledge. You know a lot of facts. You know a lot of things, but how do they relate to each other? That's what really takes a little bit of time and assimilation, and in my opinion, labs help bring that together. And hopefully we'll get the labs going here today. They said that they should be soon. I don't know what the issue was. But anyhow, we're going to talk about switching today and probably about half of tomorrow. The device that I always thought of, you know, we just plug stuff in. We just plug stuff into this thing and it works and it connects things together. And it's a pretty complex little piece of equipment. And they're not really all that expensive anymore. When we first started using them, they were pretty expensive, and we stayed with hubs for a long time because switches cost a lot more. But once you get into the switches, the improvements in the data flow and in security even helps out an awful lot, helps justify the cost. And they don't really cost that much anymore, and you can't buy hubs anymore. But we're going to do it switching. We're going to look at switching concepts, configure the basic switch operation, and then we'll do VLANs, virtual local area networks, inter-switch connectivity, which would allow us to create a VLAN in like the first floor and the fifth floor, and there we're going to configure it so that they'll talk to each other through the switching process. We're not going to have a router in there to do anything on the proper VLAN, and then troubleshoot switching issues. Troubleshooting is something, and we can talk about it. Troubleshooting is something that I think each individual develops their own methodology of how you go about troubleshooting. It takes practice. One of the things that I tell classes, and I'll tell you, told classes, and the only reason I do this again is because one of my former students who was a young kid said, I troubleshoot better than some of the senior engineers here, because you told us something in class one day is be the packet. Be the packet. Go through the access control list. Is something stopping me? Do I have a route? Can I get there? Do I have an issue? What's the flow? What are the impacts on the data as it goes from one location to the other? And when we talk about the data, we're really talking about what are the impacts on the header. The MAC address, are they correct? Is it getting the MAC address? Is it getting the correct MAC address? And this is where spoofing comes in with the ARP spoofing to be able to create a man-in-the-middle attack. The IP addresses, and in the routing, do we have routes to get there? Can I get to the location that I need to get to? Error messages help out a lot there. Network unreachable probably means we don't have a route. Host unavailable may mean that it is down, turned off, we've got a bad IP address, typo, those sorts of things. So troubleshooting, the OSI model, I really believe, TCPI, whichever one you want to use, the concept of modularity, I think, helps out a lot in that. There are a number of labs, and hopefully we get them going here pretty soon in this one. So Yesterday, the labs was, can we make this thing work? And the answer was, not really. But today, we kind of get into the labs a little bit heavier. The switches operate at layer 2, the data link layer of the OSI model, which is also layer 2 of the 5-layer TCP/IP model, and layer 1 of the 4-layer TCP/IP model. We just got too many models anymore. We used to have one, and then we had the DoD and say, okay, this is great because we'll use it when we use an IP network, and we'll use the OSI for everything else. And now we got the 5-layer and the 4-layer, but the data link layer, the place where we get the CSMA CD, carrier sense multiple access collision detection, which, and we'll go another, only applies when we're in a shared media, half duplex, Ethernet situation, and mostly we don't use Ethernet anymore. Actually, probably be safe to say we don't really use Ethernet anymore, but we still go through all of for history and for, I guess, understanding where we came from, where we're going to, we still talk about it. Switches don't have that issue. Switches don't have shared media. Switches are full duplex. Switches are really great devices. If I could only have one new device, one recent development, switch would be it. It's going to be the thing that's going to help out the network a lot. Transferring frames between adjacent nodes without any errors. Adjacent nodes means that they're in the same broadcast domain. They are connected to each other. And connected to each other, we could have a number of devices connected to machines connected to each other. And you're going to get a bad drawing. You probably can see that. I'm trying to start my pen. Here we go, finally. Connected to the devices here. We have this guy here, and then we have our ports in here. And I never can get them straight. Anyhow, whatever number of ports we have, we'll have an asymmetrical switch here. And we have devices, machines out here on it. These are going to be adjacent devices. They're going to use the MAC address in order to communicate with each other. And if we put a router out here, and the router is represented by a circle, we're going to use the MAC address in order to get to that interface of that device. So, responsible for transferring frames between adjacent nodes without any errors. And without any errors, we'll talk about the type of switching that we have. And the new switches are a lot faster. They're a lot better. We don't really have nearly as many errors as we used to have. So responsible for this, they're going to use the MAC address. The IP addresses here we only use, and they're the administrative, the temporary, the addresses. We use them basically to find the MAC address so we can communicate within a broadcast domain. So in this, back to the domains that we've had, this whole area back here is a broadcast domain. Each of these ports, since this is a switch, each of these is a collision domain. So on the switch, each port's a collision domain. If I had the famous old hub down here that says switch, but the same device that we've labeled as a switch or a hub, they look a lot alike. This actually kind of does look like a hub, but in a hub we have one big collision domain. This is where everybody can see everybody else. And it's back to the piece of coax here with the T connectors connecting these things together, shared. If I put some information on this piece of wire, everybody's going to see it. They only accept the information that goes to them. based on the MAC address. Unless, of course, we're running something like a Wireshark and we put the NIC into promiscuous mode where it's now going to see everything else. And that's where we get into what can the hackers do to us? What can the people that are trying to prove that they know more prove to us when we do those things? So transferring frames one to the other without errors, and there is some error checking at this layer. And over here, down here at the bottom, we have this thing I said, the CRC, and it is a cyclical redundancy check. FCS, frame check sequence. Actually, I guess I should wait until we get there, but now let's go ahead and do. What does that mean? If and it's similar to a hashing. And I'm just going to use a text string here for a hashing, and we'll do like Mary had a little lamb. Had a little lamb, and whether I did this text string or I go down here to a file and hashed War and Peace, and I use that because it's noted to be really big, I'm going to get a fixed length string of characters here that represent this resource here. Let me go ahead and take a snap because I want to change it and see what happens when we change just one little bit of this thing. Now let's just change the lamb here from a lowercase b to an uppercase b. And we'll do a calculation, and then I'll bring this one back over. And MD5 and SHA-1s are the ones that we use the most in the Cisco world. And the MD5 here starts out with 3050. Down here started out with 5B81. Well, I just changed one character, one letter. And I didn't change the letter, I changed the case because the ASCII, the upper and lower case, are going to be different ASCII characters. And it had a big, huge change in the hash. So the hash is, if we make even a small change in the characters, then it creates a large change in the hash. And the hash, cyclical redundancy check, the CRC, think hashing for it. It's going to use those kinds of processes, not necessarily the MD5 and the SHA-1, but those kinds of things. And that's what this thing at the end here is in the four bytes that are available for the frame check sequence that goes on here. They operate at the data link layer. We've said that multiple times. Protocols that operate at this layer: point-to-point protocol, SLIP, which is an old cable modem protocol actually, but point-to-point protocol. The other one that we're most, I won't say familiar with, but hear the most is going to be Ethernet, fast Ethernet, layer 2 protocols. Once we leave layer 2, everything's the same. A web browser, whether it's on our own broadcast domain, whether it's on a hub in a single collision domain, or whether it's on the internet, is still a web browser, whatever we're using. If you're using Chrome or Firefox or Edge or whatever else, the browser is the browser. The protocols that operate at the application layer are the same protocols, regardless of whether they're on a local area network or whether they're on a wide area network, whether they're on the internet or whether you're going to your local web server. An IP address is an IP address is an IP address, and don't say, well, on the local network we use private addresses. That's true, but they're still IP addresses. They're just not routable IP addresses, not routable on the internet IP addresses. They are internally routable when we look at those things. So protocols that operate here, and we could put the enterprise ones, and the enterprise one that we use, Ethernet, fast Ethernet, gigabit Ethernet. Each of them has a little bit different definition. Ethernet, the thing that we talk about the most, because I guess we can get more elements out of it because of the CSMA CD that we use for it. Logical link control, flow control and error control, and some framing takes place here. This is, you notice this is an insert here, the LLC. When we get into VLANs, we're going to use a protocol called 802.1q. .1q for frame tagging. Some terminology, and hopefully it'll make sense here in a little bit this afternoon. We'll do VLANs. We tag these frames so that we know which network, which virtual local area network, think IP network it's on. So it can be used token ring or Ethernet, the MAC address, the CSMA CD. I jumped from one to the other. LLC, sublayer, flow control, error control, and some framing on it. But the way we get this LLC in here, we stick it in, it gets put into this by when we put in the new framing information. And I think I've got one here in a few minutes that talks about, we'll look a little bit more at this thing. But in the MAC address, and I'll go to the next one, the MAC address layer is a CSMA CD for Ethernet. Token ring, Ethernet, all of those things are going to be part of what goes on with this thing. And I may have jumped the gun on that one. But anyhow, the Ethernet frame is encoded data link layer 2 for transmission from one node to the other node in an Ethernet network. Whether we're using gigabit, fast Ethernet, or 802.3, the original Ethernet, we're still going to have this framing that goes on with it. The real difference in those, there are some, the bandwidth we looked at is going to be a little bit different, the speeds that go on, but the media access control, how we get access to the media, is going to be the thing that really changes at layer 2. The format consists of 7 fields. First we have a preamble. It's 7 bytes. It's a series of zeros and ones, and it is used for synchronization. Synchronization information goes in here. We have the start of frame delimiter. It says, hey, the frame is starting, and there is a spacing, a timing between the frames so that they don't get confused with each other with the ones and the zeros when we look at those things. The destination MAC address. So the destination MAC address is first. And when we talk about some of the switch types here in a few slides, hopefully that will say, okay, so that's the reason it gets in there first. But we want to look at the destination first, and in some instances we're going to take the whole frame and check it to see if we have any errors, depending on the type of switching that we use. And then the source address, the source MAC address, is going to be next. The frame type identifies the next protocol. We saw some of that next protocol as IPv4 or IPv6, and then the data and padding. And this is for a standard frame. The standard frame data and padding, 46 to 1500 bytes. And this is the data area that goes in here, which is also going to include all the other header information, include the IP header information, include the TCP header information, include the HTTP, the application stuff that we have. And then the frame check sequence is the trailer. One of the reasons that they call it a frame is that the data is sort of framed with the start of frame delimiter, the 1 byte here, the SFD, and the frame check sequence at the end. If we go back to Wireshark, and let's see what we can see. You can't see all of these elements. You don't see the start of frame, the preamble, and the frame check sequence. So maybe worthwhile looking at one just quickly to see what we can see in this thing. We'll go back to the HTTP because this was the one that had the HTTP in it. It had thought it had some data. It did have some data. I clicked on the wrong one. But what we're looking at is the Ethernet frame in here. We have the destination MAC address. The MAC address itself is split into 2 parts. One is the OUI, the Organizational Unit Identifier. Wireshark resolves that. So Dell 0022 and then 19. All of the Dell, not all of the Dell, but this group of Dell Macs start with 002219. If you have that as the start of the MAC address, it's going to be a Dell. And then we have what I call the serial number or the uniqueness number. It's going to be the 1C9B. So Wireshark does resolve the OUI, and this one down here is a Belkin. The source is a Belkin router that would be in here. And we have these other things, and this is going to become significant when we talk about the EUI64 IP address. And you probably have heard of it, talked about it, maybe even looked at configuring it in Network Plus. But in the 7th bit, 1, 2, 3, 4, 5, 6, 7, it's either marked as a globally unique address or individual address, a unicast address. Factory default 0 or a 1. And what we'll do in the EUI64 is we're going to flip the 7th bit when we do that. So whether it's the factory default or whether we have modified it. It's just a way to do those things, to do the address. The type field here, IPv4. And then you can see the IPv4 tells it what's the next protocol that it's going to expect, IPv4. And IPv4, in fact, is the next protocol. And then we have the HTTP, the JavaScript. This is some JSON that I was getting for some reason. But it is now we now have the data down here at the bottom of it, the object, key stamps, anyhow, the Ethernet frame. Again, I can't see all of the startup, and this would be nice if I could to be able to show that, but the startup frame delimiter, different things that we don't see. We start with the destination MAC address, which is first, the source MAC address, the type, and then after that we have the other stuff, the data, that is a 46 bytes to 1500 bytes. Anything less than 46 bytes is going to be a runt, and anything greater than 1500 bytes is going to be a giant. So we have giants and runts in this layer 2 information here, the framing. This is what I was talking about with the addition of information that we'll use when we actually tag these things. So the original frame, the standard for the minimum Ethernet frame size, the entire frame, not the data. The data was 46 to 1500, and if you add 18 for each of these things, 18, 6 and 6 is 12, on down the line here. The header information, the layer 2 header information, is where we get the bigger here. The 1518 is going to be 18 bytes for these things. When we look at them, other tags, and it doesn't really show it completely here, but anyhow, the original total frame size, 64 bytes to 1518 bytes. When we add VLAN tagging, when we start configuring VLANs, we have to be able to keep track of them, and we do that by adding a tag. And then we get a little bit more information that's available in here. For instance, once we add this tag, we can now do quality of service. We can assign some things a higher priority than other things. But anyhow, the objective of this is we add 4 bytes. We add a 4-byte field here so that the maximum is now increased to 1522 bytes in the entire frame, not the data portion of this, but we're talking the frame itself. Here we're going to go. The frame from one to the other is where this 1522 bytes is once we add this tagging information, and we'll do the tagging when we do VLANs this afternoon. So we add the information, we now have different numbers for the runts and the giants, and different numbers, and then what is it, where is it, those sorts of things. You know, how much of it are we talking about? The data, typically the data portion here didn't change. The data portion here is still going to be 46 to 1500 bytes of data is what we're going to put into the frame. The tagging, the total that's changed is the total frame size. So data is going to stay the same. 1500, the MTU, the maximum transmission unit. 1500, you've probably seen that before. MTU, 1500, maximum transmission unit, 1500 bytes is what we're looking at for these things. The MAC address, a hardware identification, which is also the MAC. It is assigned on the NIC, 48-bit serial number programmed in when the NIC is manufactured. Also call the BIA Cisco term, burned in address. I know it was on the questions this morning, and probably should have waited. Some of those I jumped the gun on a little bit. But the BIA, the burned in address, is the MAC address. Cisco term. You'll hear it called both in those, the BIA or the MAC address. It is, and as we discuss, it identifies the device that should receive the data frame, and is split into two sections. The OUI, organizationally unique identifier, vendor assigned, serial number, whatever you want to call it, but a unique identification. If you have two devices, been there, done that, did it with virtual machines, where we messed up and copied instead of saying that we moved, or said we moved instead of copied, because if we moved, then it didn't create a new MAC address for the device. If we copied the virtual machine, it would generate a new MAC address. So we put these things, we're doing a course, we put these things on the same network, and boy, communication was just erratic. We try to ping a device. Sometimes it'd work, sometimes it wouldn't work. We try to communicate with something, and generally it wouldn't work because the systems didn't know where to actually send it, because now we've got two devices that supposedly have unique addresses that didn't. And what we did was use the ARP table, and when we do ARP, we'll look at the ARP table. We finally looked at the ARP table, and it says, oh, this IP address has got this MAC address that you're seeing here. Oh, this IP address has got this MAC address that you're seeing right here. And it's not working out so well when you do those things. So it is split into two sections, identifies the devices, and they do need to be unique. If they're not, we can have a situation. And unique within a broadcast domain, honestly, because that's where they're going to be used. And we're going to look at what happens. We're going to have some frame rewrite as we go from one location to the other, as you might expect, because what the MAC address is used for is to get to the next device, get to the next attached device. If it's within a switch, within a broadcast domain, to get to the device that's there. If we're getting to our router, to get to my router, to get to my default gateway, it's then got to change the MAC address to get to the next router. To get to the next router, that stuff has to be rewritten, and that's going to change the cyclical redundancy check, the frame check sequence, the hashing. It goes on from one to the other. All that has to be accounted for with these things. So the content addressable memory, the MAC table, switching table, forwarding table, lots of terms here. And back to the comment earlier, just got to learn the terms, and there are a lot of them, and it does take a while to do that. The MAC address table for these things is created dynamically by each switch using the source addresses to build the MAC address table. And I want to go back to the demo that we did yesterday and do it again just to try to reinforce, I think is a good word, what actually happens in this thing. Let's see, MAC address table demo. And in order for this thing to start, first thing I want to do is go into simulation mode, because I don't want it doing stuff for me early on. And we can use the show command here. And let's look at the show MA question mark, MAC or MAC address table, MAC, and if I try the tab, it doesn't work. If I do the dash, now the tab works, the completion. So show the MAC address table. We have some here that are dynamic, which means that these are the ones that we detected yesterday. So now I can clear the MAC address table, and the up arrow key will recall commands so that you don't have to type them in every time. So now we have this thing gone away. I want to delete this one, and then we'll go in here and we can just use a packet here, and we'll ping from one location to the other. And let's be sure that we still don't have anything in here. So we'll use a show MAC address now. See, it's already messing me up here. Clear the MAC address table. Now let's see if it will do that. The system and the simulators kind of don't always do things. But when we now go into the switch, and if it hasn't helped me out here, when I do the show MAC address table, I have the one which is, remember, 95D5, Fast Ethernet 03. So we can go into this guy and do an IP config all, and it is the MAC address of the device that's sending the frame. So the source MAC address, actually that's not the MAC, here's the MAC address, that's the IPv6 address. And when we look at it, this is going to be we look in here, it's built off of it, the FE80. We'll talk about those when we get to IPv6. Don't want to do that here, but just look at it. It's similar here. We have the MAC address here that is now the same MAC address that is in our switch. Since it doesn't know where it's going, the destination of this thing, it floods it out all of the ports except the port that it came in on. Doesn't have to flood it out the port it came in on, because it now knows what MAC address is on that port. And yeah, you can't have more than one MAC address assigned to a port. Down here, we would have on this one, we would have both of these on them. And the hub, it's always going to go out, went out both ports here, and now we're at where we should be. The response comes back. The rest of them don't respond, obviously, because it wasn't to them. It wasn't to their MAC address, which had to be resolved by the ARP protocol, the address resolution protocol. Notice on the hub, it went out all the ports except the port it came in on. Now when we go back, we have another frame that's entered this switch. So we now have two MAC addresses. Uses the source MAC address in order to build the MAC address table when we do those things. And since it now knows what MAC address is on this port, or knows the location of this device, it then forwards it directly to that device. If we go through this again, looking for the destination MAC now, sends it straight down. The hub still goes out all of the ports except the port it came in on, because there's one giant collision domain down here. The switch, each port creates its own collision domain, so that we can have a lot better communication that goes on. We don't have collisions. You should not see collisions in a switched network. If you do see collisions in a switched network, you need to look at the duplexing and the bad NICs, bad ports things like that that are going on with it, because the device itself, when you do that, there should be no collisions, because it keeps track of these things in the MAC address table and only sends it to the location that it's destined for. And if all you Security Plus guys and security guys, this is a pretty big advantage. Back to the who sees everything. Nobody sees everything now. You only see the traffic that is to you. You're going to see all the broadcast traffic, but that's probably not going to be anything that's all that secretive. But now we've created some isolation that you, the devices, you, me, the devices, the computers, the traffic only goes to the device that it was intended for. It doesn't go out there on that piece of wire, that piece of coax, so that everybody that's out there can look at it, can see it. We only see the traffic that's to us and the broadcast traffic. So in this thing we have the source addresses, the source MAC address, the VLAN association, the VLAN that this thing goes on, and we'll do VLANs this afternoon. When we do that, each VLAN is going to create its own broadcast domain. These are still going to be collision domains. A collision domain is created on each port of a switch. How it was learned, and this doesn't mean a whole lot right now, it will a little bit later when we do port security. Of course, a little bit later, it'll be next week when we'll do port security on these things. It can be dynamic. Basically what we can have here is dynamic or static. We could make these static if we went into the device and assigned, manually typed in a MAC address associated with a port, put it into the tables. Then it would show up as a static, which means that we typed it in. My problem with typing it in, because you see me type, is that I make typos. I make a lot of typos. And then after that, the port that it's associated with. So now we know the MAC address, how we figured it out, how we got it. And the dynamic is significant here because they don't stay forever. They will time out. And the timing out is generally whether it gets reused or not. The timeout timer, the default timer, is 300 seconds, 5 minutes. If the address is reused, depending on how we configure the switch, it could be as absolute or it could be on a reset basis. When we reuse it, then the timer gets reset for 5 minutes and does its countdown. If it's an absolute, then it gets set for 5 minutes and times down. When it gets to 5 minutes, it gets flushed out of the MAC address table. It's not going to be there anymore. So it is break time. Questions? Or do you notice that I have a knack for taking a break just before the last slide of a section? And that's Mac learning, or say Mac learning and aging for this thing. When we go here, every dynamic MAC address in the table, and an activity timer is stored, and this is what we talked about. The timer indicates the duration for which the address will remain in the table when no frame is received for that address. Static addresses don't have an inactivity timer by default. You can, and this one kind of surprised me, you can set a timer manually on a static address. Don't know why you would want to do that, but you can. Typically, you put the static address in because it's going to be there. And this is one of those, the static address, we could put it in for maybe a server that's attached. It's always going to be there. The reason that these changes, what happens if a NIC fails? Then it's not going to be there. The MAC address tables also have limited memory, like everything else does, limited storage, so you can overfill them. One of the hacker techniques is a piece of software called MacOff, probably not anymore, but it used to be one where you try to fill up the MAC address table. Once the MAC address table is full and it can't learn any new addresses, the switch reverts to being a hub so that everything sees everything. And that's what a hacker would want to be able to do in order to be able to compromise the network for those things. When a frame source address is matched against the MAC entries, the MAC is found, the switch resets the inactivity timer. If it's not found, the switch sets the inactivity timer to 0 for new entries when we do those things. If it's used, the inactivity timer to identify the inactive interfaces, and we can do that. Very old entries are deleted to ensure that it's up to date, doesn't run out of memory. We move things around on switches, and what should happen is if we move from one port to the other and it detects that particular MAC address, it simply moves it in the MAC address table to the new location, so that the new location is going to be used for what goes on with it. We have